Hello students, in this module, which is part 7 in our series on differential equations, we will try and solve an initial value problem, partial differential equation uh, with initial condition and boundary conditions, which is an initial value problem, and we will try to solve it in a semi-infinite domain. So we'll consider the usual unsteady, diffusion or heat equation, right? Here U may represent a temperature or a concentration of a species, but the domain that we are interested is this, and then time is also like this. Okay, so we are given an initial condition, that is the temperature at time t equal to 0 at all x is 0, and we are given two boundary conditions. The temperature at x is equal to 0 at time t greater than 0 is g of t. Okay, and the other boundary condition is that as x goes to infinity at all times t greater than 0, the temperature is 0. So the objective is to find how the temperature varies as a function of space and time at all t greater than 0. Okay, and we know that Fourier transform is defined only for functions in the domain minus infinity to infinity. You can use the Fourier transform, but here we have a semi-infinite domain from 0 to infinity. So Fourier transform is not possible to use in semi-infinite domain. Semi-infinite domains. Okay. So what we instead do here is we use the Laplace transform to transform the time domain. Okay, so we use the Laplace transform to transform the time domain, and in that process we will eliminate the time derivative, and instead of a PDE we will end up converting the PDE in x and time to an ODE in x, and that is relatively easier to solve. So what we first do is to take the Laplace transform of the entire PDE. What you do is 0 to infinity, you take the entire PDE multiplied by e to the minus st dt. The left side has alpha squared, which is a constant, 0 to infinity, partial squared u by partial x squared, e to the minus st dt. Yes, the right side has 0 to infinity, partial u partial t, e to the minus st dt. Now this is an integral over time, whereas the derivatives are over x, so I can write this as x squared integral 0 to infinity u of xt e to the minus st dt is equal to, now the Laplace transform of a time derivative is something that we are familiar with, s times u bar of xs, where u bar of xs is the Laplace transform of u of xt, right, times or minus u of x at time t equal to 0. Now let's look at the left side. Now this object out here is actually the Laplace transform u bar of xs. That's the definition of Laplace transform of u of xt. Now the initial condition says that u of x at time t equal to 0 is 0, right? At all of the half space the temperature is 0. So what we are left with is therefore a simpler equation, an ODE. Now I can convert this to d squared dx squared, the ordinary derivative, because the resulting equation is a differential equation only in x. Although s is there, it's u bar is a function of two variables, there is no differential in that. So you can effectively think of this as an ODE by dx squared minus, okay, let's s by alpha squared u bar, okay, of xs is 0, right? And this must be supplemented by boundary conditions. The boundary conditions are also transformed, Laplace transformed. Now let's first consider the boundary condition as x goes to infinity limit x goes to infinity, u bar of xs is nothing but limit x goes to infinity, 0 to infinity, I can interchange the integral and the limits because integral is over time, x goes to infinity, u of xt e to the minus st dt, and this is 0. Okay, so that means that this is also 0, that u bar of x tends to infinity, s is 0. Okay, this is one boundary condition. Now if I solve this differential equation, I get two solutions. U bar of xs is a e to the root s x upon alpha plus b e to the minus root s x upon alpha. Now as x goes to infinity, u bar should go to 0. That means that the constant a must be 0, because this is anyway going to decay as because it has a minus sign, whereas this is not going to decay unless the constant has to be 0. Constant is made set to 0. Okay, so we are left with only one more constant. So u bar of xs is b e to the minus root s x upon alpha. Now let's say the initial condition, the boundary condition at x equal to 0, you must transform the initial the boundary condition. See, we are given that u of x equal to 0 t is g of t. If you Laplace transform this, u of x equal to 0 s will become g bar of s. So you have to do a Laplace transform of that. So this becomes g bar of s. So if I use this boundary condition, this is a known function. Okay, if I use this boundary condition, I'll get u bar of xs is equal to, if you put x equal to 0, this becomes 1. So all you are left with is b, and b must be equal to g bar of s. So g bar of s e to the minus root s x upon alpha. So we have solved for the Laplace transform of u of xt in terms of u bar of xs. You have to do an inverse transform, inverse Laplace transform. Now first you should note that it's a function of it's a product of two functions of s, g of s and e to the minus root s and so on. So we have to use convolution theorem in Laplace transform, very similar to the convolution theorem of Fourier transform we discussed in the previous module. So I won't go into the detail. Essentially, the inverse Laplace transform of two functions of s will be the integral of the product of the original functions in the time domain. Okay, so this is x by 2 alpha root pi integral 0 to t g of t minus tau e to the minus x squared by 4 alpha squared tau by tau to the 3 half d tau. So in general, this is the solution to the problem. That is, if you give us a function g, then we can substitute this and then find the evolution of the temperature. Now let's take a special case where g of t is just a constant. You are not changing the temperature at x equal to 0, it just remains a constant. In which case the solution can be simplified further. Okay, so u of xt now becomes t naught by root pi x by 2 alpha 0 to t e to the minus x squared by 4 alpha squared tau by tau to the 3 halves d tau. Okay, now I'm going to solve this further by changing variable. I'm going to assume that x squared by 4 alpha squared tau is equal to zeta squared, or zeta is x by 2 alpha root tau. Okay, sorry. So, or tau can be written as x squared by 4 alpha squared zeta squared. So d tau becomes x squared by 4 alpha squared minus 2 1 over zeta cube d zeta. Just by differentiating this with respect to zeta, you get this. Alright. Now if I substitute all this out here in this equation, okay, so I'm going to say u of xt is t naught by root pi. Okay, I'm going to write this. So remember that zeta squared is x squared by 4 alpha squared tau. So tau goes to 0, zeta goes to infinity, and tau goes to t, zeta goes to x by 2 alpha root t. Okay, in the upper limit is tau goes to t, so this is x by 2 alpha root t. Now I'm going to pull this inside, so this becomes e to the minus zeta squared, and then you have 1 over tau to the 3 halves, you have x over 2 alpha. Now instead of d tau, I should write from the discussion we just had, minus 2x squared by 4 alpha squared d zeta by zeta cube. Okay, now u of xt then becomes t naught by root pi infinity to x by 2 alpha root t. Okay, now if you look at this, this becomes e to the minus z squared. This is, and I'll pull the minus 2 also outside. Okay, so this will become x by 2 alpha root t whole cube, because you have x squared by 4 alpha squared, which I write as x by 2 alpha the whole squared. There's another x by 2 alpha, and then there is t to the 3 halves. Everything can be clubbed. Now if you realize, this entire thing is just z cubed, so this 1 over z cubed cancels with this, and finally giving u of xt is minus 2 t naught by root pi integral infinity to x by 2 alpha root t. Okay, e to the minus zeta squared d zeta. I can absorb the minus sign and change the limits. This is x by 2 alpha root t, right? And I get simply t naught 2 by root pi, okay, to infinity e to the minus z squared dx. Okay, now there is a special function called the complementary error function, which is related to the error function we discussed in the last lecture, which complementary error function of x is x to infinity e to the minus z squared dz, and this is the same as 1 minus error function of x. So error function c of x is 1 minus error function of x. If you look, oh sorry, there is a 2 over root pi. If you look at this, this is identically u of xt is t naught times error function of c of x by 2 alpha root t, which is t naught 1 minus error function of x by 2 alpha root t. This is the solution to the problem for the special case when g of t is just t naught. Okay, otherwise you have to use the general integral expression. Now so this is an example of how even though we could not use the Fourier transform in the spatial domain, we use the Laplace transform in the time domain to convert the differential equation to an ODE and solve for the ODE in space, and then you inverted the Laplace transform to get back the original solution in terms of space and time. Now one important comment that I would like to make is that if you look at transport phenomena, you solve this problem of unsteady conduction in a solid or unsteady diffusion in mass transfer. You use the method of what is called similarity transform, where you use a clever combination of variables, where you say that x by 2 alpha root t is zeta, and you use this variable to convert the PDE to an ODE. That's a different method, because that method relies on a particular physical idea, Whereas here even if you were not aware of that method, we were able to solve this unsteady diffusion equation or conduction equation using the method of Laplace transform. Thank you.